Hello and welcome back. So, in this video we will look at data preprocessing or data normalization techniques before you start using them as input to some of the common machine learning algorithms. Okay. So, what I will describe now is most often used, the commonly used technique, and it is called the Z-score normalization. I will just go through what is actually done and then we can see why we actually have to do it. Okay. So, let us say we have m data points, which is for training data points. So, this is just to be m training data, and there are n dimensions. So, which is basically n dimensions are or features. So, incidentally these techniques are also known as feature scaling techniques, right. So, what we typically do is that we make them all 0 mean. So, which means that if you have, let us say we denote our data points by x, right, and look at, let us say we are considering a feature x 1, right. So, then we calculate the mean for that feature mu 1, and we have this I, which is the data point index from I equal to 1 to capital M. So, we have mu 1 and we just set x 1 to x 1 minus mu 1. Okay. So, we do that for every feature that is available in the data set. So, now all the data points are 0 centered or 0 mean. The next step that you typically do is to divide this. So, I will denote this by x 1 cap. So, that just to be different. Divide the mean subtracted features by the variance, this is actually a standard deviation, the square root of the variance is what we want to do of each feature. So, if we can calculate, so once we have done the 0 mean, then the standard deviation we will call them sigma 1 squared, nothing but the mean of the. So, if we have I equal to 1 to m, and then each of these I and then squared. So, of course, in the previous summation I left out the normalization by the total number of data points, of course. So, that please amend the mean. So, I have to divide by m, So, this is the, since we have subtracted the mean out, this will work. So, we take the square root of that. So, it will be just sigma 1, right. So, we take sigma 1 and so we get x 1 cap goes to x 1 cap divided by sigma 1. Okay. So, that is the process. So, you calculate the mean. So, sorry I left out that m in the first part. We calculate the mean for each feature independently over the training data, not over the entire data set. Now, we have split your data into training, validation and testing. So, you calculate the mean over the entire training data, subtract the mean for each feature from the individual data points and divide by the standard deviation of each of the features. Okay. So, this is the general the most often used data normalization technique. This is of course assuming that your data is Gaussian distributed, which might not be true most of the time. So, what does this accomplish? It brings your makes your data points as a 0 mean and unit standard deviation or unit variance, right. So, why is this essential? Why do we want to do that? So, before we go there, we just look at some what it looks like after the normalization. So, I have just considering two features x 1 and x 2, okay, and x 1 ranges from 1 to 1000 and x 2 ranges from 10 raised to 3 to 10 raised to 6. So, if you want a solid example, you can think of this as the square feet or the area of some living space, apartment or plot of land, and this as price of that living space. Okay. Very cheap by today's standards, price in rupees or whatever denomination you want to currency you want to choose. So, if I plot these two, so again x 1 here and x 2 on that axis for all three plots, that is what it looks like, since they are both drawn from random normal distribution. I look does not look anything spectacular, but so I just want to show you what happens after the normalization. So, if I subtract the mean out from x 1 and x 2, you can see that they are 0 centered. Okay. So, and so the 0 is here kind of, and yeah, right there. Okay. centered, but you can see that the x1 is in this case this is the span of x1, if you can think of it as the the scale of x1 is in this direction and the scale of x2 is here. So, if you look at it, if you actually have to look at the numbers, this is in the thousands and this is of the order of 10 raised to 5 or 10 raised to 4. So, this height, the range over which this spans is much higher than this range. Okay. So, if we actually divide by the standard deviation for each one of them, you can see that their ranges are also similar, right, minus I think minus 2 to 2 for both the x1 and x2 parameters. Okay. This is after we divide by standard deviation. So, why do we need to do this? So, if you recall, let us say if you are considering a neural network, let us say I am just going to look at 2 neurons just to show you what will happen. Let us say the input is x1 and x2, right. So, you have like that, right. So, the problem here is that, so we in here we have terms like w1 x1 plus w2 x2, right, this term will appear often, right. So, when you look at these kind of terms, if you are not normalizing, you will see that x1 is much smaller than x2 by a factor of 10 raised to 3. So, but during optimization, then in order for the network to converge, then the weights have to be adjusted accordingly. So, you would expect that the weight multiplying the larger value would be much smaller, like let us say by same order of magnitude. So, it turns out that this kind of optimization is much harder to do or typically will not converge or would be very slow to converge. So, because when you are inputting, you are saying that x2, because it is working with numbers, you are saying that x2 is more important than x1 because it takes larger values. Now, if you think that all your features are equally important, then it is important to do this normalization, because it brings them in the same range of numerical values and it helps convergence faster. Okay. The optimization is easier this way using gradient descent, right. So, because we have sums of this form, wherein so because this will be the input to your sigmoid function or the nonlinearity. So, then the larger term will tend to dominate all the time. So, to prevent that from happening, of course, during optimization W2 would be adjusted so that x2 does not dominate, but of course, that is a difficult problem for optimization. If the x1 and x2 are the same range, then the problem is much easily solved. Okay. So, that is the reason why we do this normalization. If all your data points are in the same range, you need not sometimes do it again, but then also depends on what your output is like and all that. So, for instance, if you are doing a conditional output, probabilistic output, let us say it is a classification task, it makes sense to squash all your inputs within a range 0 to 1 or within this or do this kind of normalization. Same thing with regression. Okay. So, if your inputs are bounded, then you can have a bound on your output also. So, it makes some sense to do this normalization for many classification or regression tasks. So, there are other techniques which we will look at. There is something called the principal component analysis, where you can reduce the dimensionality of data and also decorrelate the data. So, for instance, in the previous example I said, okay, you can think of the smaller feature as the square footage and the larger variable as the price. Obviously, they are correlated, right. So, there will be lot of such features in your data set which might be correlated, and the principal component analysis techniques helps to decorrelate also. Now, we will look at this at a later lecture in the coming weeks, where we will talk about what PCA is, and then I will show you how we can be used for pre-processing data for machine learning algorithms. Of course, there is other scaling we can do here. We did the z-score, wherein we subtracted the mean divided by the standard deviation. You can scale your data to lie between -1 and 1 or between 0 to 1, okay, depending on your application. This can be done. Okay. These are also valid pre-processing techniques. I would not call them normalization, but pre-processing techniques that will help you. Okay. So, these are what we have looked at is the most fundamental or the often used pre-processing technique, and it is typically done for many any kind of input. You can do that even for imaging inputs or any kind of real valued inputs. Okay. So, from here on we will look at so this is again for the input layer. So, this is for the input layer. Okay. So, this is your data which is your, this is goes to as input to the first layer of your algorithm, in this case a deep learning algorithm. So, what happens in the intermediate layers, right? So, these are these kind of techniques applicable there too, and how would you go about implementing them. So, this will be the topic of our next lecture, where we will look at a very at this point in time an often used technique called batch normalization, okay, and that seems to help quite a bit for faster training and convergence and gets rid of many of the problems. Okay. So, one of the things before we go there, one other thing that I think I pointed out, but just reiterate, is that if you have very large features feature values, it is quite possible that you will hit the saturation of your non-linearity, okay, especially if you are using sigmoid. That can easily happen if the weights also blow up, okay, that is a possibility. So, it gets a very, so let us say x2 gets a very high weight, then you will end up in the saturation regime and there will be no learning. So, that is typically why you don't want, you want to have all your inputs to be scaled within certain ranges. Okay. So, how do we address this when it happens in a hidden layer? Okay, that can think of it that way, that is a problem too. So, we will look at this batch normalization, or batch norm as it is called, batch norm, which acts as a layer, one of the layers in a deep network, and how it helps in faster convergence. That will be the topic of our next video. Thank you.